In example 6, we have r times the cosine of theta equals 9. And I might not be sure off the top of my head what that looks like on Desmos, but I could check it out if I wanted to. So if I have r times the cosine of theta equals 9 on our polar grid, it looks like we have a vertical line there. So I should be expecting something in the form of a vertical line when I change it into rectangular coordinates. So let's think, what do we know about r times the cosine of theta? Well, that's one of our formulas. R cosine theta is x. So I can substitute in x and we get x equals 9. And that should make sense to us because that is the equation for a vertical line. It's always x equals a number. And that's actually as challenging as this example is. That's it. That's your final answer. Example 7. R equals 4 times the cosecant of theta. We can look at that on Desmos. So r equals 4 times the cosecant of theta is a horizontal line. So our goal is we should be getting something that's in the form of a horizontal line. We know that's typically y equals something. So let's see if we can get there algebraically. Now the one thing that's challenging about this problem is that I see an r and I see a cosecant of theta, but in the formulas that we have on the front of our packet, I don't see cosecant anywhere. But I do have a formula that uses sine, and we know sine is the reciprocal of cosecant. We know that r times the sine of theta is y. So maybe if I can rewrite this equation first to use sine instead of cosecant, that will help us. So let's think of it. R equals 4 times, well, cosecant is 1 over the sine of theta. So you could also think of this as 4 over the sine of theta, if that would be more helpful. Now, if we know r times the sine of theta equals y, then maybe it's beneficial to us to move this sine of theta to get over on the other side. So if I multiply both sides by the sine of theta, then on the left side we have r times, the sine of theta equals 4. And that allows me now to substitute in a y. So we would get the equation y equals 4. And we know this is a horizontal line, and that would be our final answer. So let's go on to that last example. Express the equation y equals negative root 3 over 3x in polar coordinates. Well, hopefully you can see that this is a form of y equals mx plus b. There's no plus b really there, so it's plus 0. It's going to go through the pole. So we're expecting a final answer here in polar coordinates that's going to still be a line. So think about what we know. Right now we have an equation with y and x. So one possibility is we could go through and we could say, well, let's replace y with r times the sine of theta. And then negative root 3 over 3 would stay put, and we could replace x with r times the cosine of theta. Typically, when we're changing into polar coordinates, we want to get r by itself. But if I try to move this r, for example, over to the other side by dividing by it, well, then these r's will cancel out, and so will these. So this seems a little bit different, and I'll walk you through what we need to do. But now we have the sine of theta equals negative root 3 over 3 times the cosine of theta. Well, I want you to think about when you are in rectangular coordinates, if y goes away, because we're very used to having y equals something, if there's no y in the formula, then we end up solving for x, and we end up with x equals something. So in polar coordinates, we typically have r equals something, but if r goes away, now we need to get it in the form that it's theta equals something. So the point here is I need to get theta by itself on one side of the equation. So in order to solve for theta, I need to move them so they're on the same side. So I'm going to go ahead and divide by the cosine of theta on both sides. Sine of theta over the cosine of theta, I could think of that as the tangent of theta, and this is going to be helpful because we are very familiar with the unit circle. If I need to get theta by itself, I'm essentially taking the inverse tangent of both sides, right? So if I take the inverse tangent of the left side, the inverse tangent of the right side, these cancel out, so I have theta equals, and then we need to think about the inverse tangent of negative root 3 over 3. Well, what angle has that tangent, negative root 3 over 3? It's always going to be something where, remember on the unit circle, it's something that has a denominator of 6. So we have the pi over 6. Over here we have 5 pi over 6. We have 7 pi over 6, and we have 11 pi over 6. We need it to be negative. Well, that happens in which quadrants? We know that's in the second quadrant and then in the fourth quadrant. So there's actually a variety of ways that you could write this. You could say that theta equals 5 pi over 6. That would be a correct answer. You could say theta equals 11 pi over 6. That would be a correct answer. Negative pi over 6 would be a correct answer. These are all the same equations. And the reason why is because if you think about plotting theta being 5 pi over 6 in the polar plane, you would have any r value, but then your angle being 5 pi over 6. Well, that's going to have on that polar plane any of these points along 5 pi over 6. That would be any of the points that have a positive r, but then a negative r would go this way. So it's this line, which we can see would have a negative slope in rectangular coordinates. And hopefully you can see why this is the same as if we use theta being 11 pi over 6. So if you had any r with 11 pi over 6, this side would be where r is positive, and then over here would be where r is negative. So if we look at these graphically, we can see how they're the same things. Here's our negative root 3 over 3 x equals y. So this is in our rectangular grid. And then in the polar grid, unfortunately, it doesn't really want us to graph it. If you try this on Desmos, it tells you that you can't graph theta as a function of anything yet. So we've stumped Desmos, but hopefully you can see why, when I explained it over here, why those are in fact the same line.